Hello and welcome to part 2 of the Introduction to Image Velocimetry. These workshops have been designed for students who want to look at using image velocimetry to capture their own and process their own surface velocity data towards their own research. So part 2 has been designed to explain the things that you've looked at previously, but they're the things that you kind of have to look out for and plan for your own velocimetry sites. So this is all taken from research that's currently available online and it's a little bit through practical experience. The idea for this part is to help you understand what the key considerations are. And when you want to go out and capture some image velocimetry data yourselves, these are the sort of things that you'd have to think about. It's important that you're familiar with these methods before you try to capture the data so that you understand the processes that you have to go through later on, such as stabilization and orthorectification. So to do this, I decided it was easiest to break the full process into 4 key stages that generalized studies typically go through. So the first one is being capture optimization. Then we're going to have a look at the 3 pre-processing and processing stages, and then we're going to finish on some post-processing steps of what you can do with your data. So those 4 key stages that we've just defined, they've been broken down a little bit further so that we can talk about specific processes. And I'm just going to touch on some of the most important pieces of the research that I found, just to help people optimize their workflows. And then when it comes to using image velocimetry techniques such as PIV and PTV, they have a better understanding of how it works. So starting with stage 1, which is capture optimization. This was further broken down into 5 subheadings, and we're going to start with ground sampling distance, or GSD for short. As I discuss each of these subheadings, I'm going to try and go into a little bit of depth for what they are, but the main focus will be what they mean for velocity techniques. I'll provide some figures and diagrams where possible, all of which will have come from the paper that this work comes from, which was published last year. So to start with, we're going to look at GSD, which I previously said is ground sampling distance, which is simply the distance between the centroid of 2 adjacent pixels. So that can typically range between centimeters through to tens of meters if you're using satellite imagery. Without changing the hardware, there's 2 main ways to improve GSD, and that's either decreasing the distance between the camera and the subject site, or you can increase the resolution of the imagery, so increase the amount of pixels that are actually in the frame. So regarding the height, it depends on whether you're using a fixed camera or a mobile camera as to whether or not you can change it. So fixed cameras can be a little bit more complicated to install and optimize in terms of their angle and their height. And it very much depends on the level of the access that you have to the site. So if you're working in an environment where it's quite treacherous or there's a lot of trees, you might struggle to get the camera at a decent height enough to see the river. Mobile stations are a little bit more flexible regarding their height and therefore should be optimized to fly as low as possible, really, while still capturing the full study area constantly. So for fixed stations, you might not be able to greatly reduce the height of the camera, but you could use zoom lenses, which could zoom in on the subject site a little bit more, and that will increase the focal length of the camera, which can have the same impact as decreasing the height. One thing to quickly note here is the possibility of stage increasing between the river and the fixed cameras. So if you have a large increase in stage, then it can actually hinder how much of the river the camera actually sees if it's too low down. And with quite a narrow angle, it will just shrink down the area that it can see. There's little research in the way of defining the best resolution to use. So like I said previously, you can increase the GSD by increasing the resolution, but we're not 100% sure if that's the best way to improve results. Research does show that increasing the resolution severely increases the processing time as well as your storage requirements, but doesn't necessarily improve the accuracy. It's hard to suggest how to optimize for GSD without considering all of your site characteristics. The best way to go around this is to look at the constraints that you have on your study. So how much storage do you have? What platform are you using? And how much data are you going to be transporting around from the site? So ultimately, you need to play about with all of these variables until you achieve the best possible GSD with the lowest possible resolution, unless processing and storage isn't a consideration in your study. But that's quite rare, especially for studies lasting quite a long period of time. If you're only doing a study for 1 day or a single event, then you can get away with it. So these are 2 equations that I've found or I've come up with. The one on the left is for capturing videos at angle nadir. So that means there's no angle introduced in either direction and it's perpendicular to the surface. Whilst the calculations on the right let you introduce either an angle vertically, horizontally, or both. So these can be really useful when you're trying to work out what height you need to set your camera to achieve a certain GSD. Now, the one on the right splits the image into 4 quadrants and it will give you an average GSD over each quadrant. These have been put together onto a spreadsheet and I'll show you that now. So this is the tool which is available on GitHub, and you just put in some of your basic camera parameters, so such as your focal length, your sensor width, some of the angles that you're trying to introduce to it, your resolution as well, and it will just tell you on average over each quadrant what the GSD is, so that you can find this online. There's a link on the slide. Okay, so next up is traces, and traces are basically the part of the video that the algorithms will track. So for good practice, traces need to be present on at least 10 to 30% of the surface of the river, and it also needs to remain visible and traceable throughout the sequence. So sometimes where you're not doing like a continuous study and traces aren't prevalent at all times, it's possible to actually use artificial traces such as bark or decomposable polymers, just so long as they've got to be passive to the flow, they're easily distinguishable, and they have no effect on water quality. So that means that they're light enough to go along with the surface velocity, they're white where the background is black and black where the background is white, and they don't have any effect on the ecology. So for a tracer to be good in shape and size over the time of the sequence, it's typically got to be larger than 1 pixel of the image, which goes back to the GSD that we were talking about previously. For artificially placed tracers, ideal particles should be kind of like ellipsoidal and between 2 to 5 pixels in size. They've been shown to perform best. So with capture rates, any standard video camera tends to have a decent enough capture rate during the capture optimization stage that it's not much of an issue, as most of them will capture at least 15 frames per second, which is more than enough for most image velocimetry techniques. The key to the capture rate during capture optimization is to just ensure that the frame rate is consistent throughout the video sequence. Usually that isn't a problem, as most video camera suppliers will provide timestamps on the videos to each frame, so that can be double checked. And there's no real limit on what type of video camera you can use to capture the imagery, but you should note that the video sequences can take up a lot of storage space with raw imagery. So if you use IP cameras, you also have to consider the constraints that you have with such things as bandwidth when you're transferring imagery. Finally, for capture optimization, I just want to quickly touch on environmental conditions at the time of your capture. So some of the environmental conditions that I focus on is the presence of wind, rain, and glare within the imagery. Although that these have been mentioned in previous case studies that you'll find online as limiting factors, there's little to no research in quantifying the impact that they actually have on results, and are usually limited by not being present in the data for a majority of case studies, which isn't always useful for us when we're trying to actually do some of our own research or use it in industry. Some of the typical factors that I've hypothesized to be associated with each environmental condition are, for wind, the false traces and tracer disruption, so that's ripples on the surface created by wind and not velocity. So rain also blurs the image, and you can sometimes get false vectors and again more tracer disruption. And then finally, for glare, the impact that brightness variation has across the image. Sometimes you can lose traces as it goes into an area of, say, light to dark. But that's something that's being researched a little bit more and we're not 100% sure on. So there's 2 typical ways of capturing data for velocimetry, and that's either using a fixed camera or a mobile camera, and that can be a UAS, it can be a mobile phone, it's anything that doesn't sit in place and captures data over a long period of time. So you can use fixed or mobile cameras to capture the velocimetry data, but each is used in different circumstances. So a fixed camera can be installed to capture data over long periods of time, usually for studies that involve discharge rating curves or anything to do with like morphology. But then using UAS systems to capture image data simplifies a lot of things, as naturally images are captured at that nadir angle, that perpendicular angle, and that reduces the stretch of pixels that's introduced with the angles, and that goes back to GSD and that average GSD across a quadrant where there's an angle. But it also helps the operator capture data at areas that might be too dangerous to traverse and set up a fixed camera, especially where there's circumstances of extremely high flows over a period of time. The second main stage of generalized image velocimetry is that of pre-processing. So pre-processing takes the optimized captured data that we've got and it begins manipulating it ready to be processed by the program and the algorithm. So this involves three main stages, which is image stabilization, orthorectification, and image manipulation. It's worth to note at this stage, however, that orthorectification can be done at a later stage, and some softwares do implement it at a later stage. But for the purpose of this presentation, I've decided to include it within the pre-processing stage. For image stabilization, there's two main methods, and that's manual or automatic. So manual methods rely on the selection of static reference points, which are then automatically processed to determine a displacement in frames. So those reference points could be corners of buildings or trees or poles or posts, anything like that that stays stationary throughout the video. For automatic methods, the features and the displacements are both selected and tracked using binary feature matching techniques, which is all done in software. For most stabilization transformations, you need at least 4-point pairs for a full projective transformation, which also takes into account the perspective deformation. It's also worth to note that if there's a vast amount of movement within the frame, the programs can actually be set to update the reference frame per number of frames, or you can simply use the first frame as the point of reference, which basically means you're either going to end up with a video where it's stabilized to the first frame and the rest of the frames that move will all fit that first frame, or you can update it every end frame and then the video looks like it's moving a little bit but actually isn't in the key areas. Without sufficient stabilization, displacements can be skewed, and even stationary objects such as the bank can be detected as moving and given a velocity vector. Second stage to image pre-processing is orthorectification, and it's quite an important stage. This can be done at a later stage, like I said, and it is done in programs such as River at a later stage, but we're going to be looking at what we call explicit orthorectification, which is simply the orthorectification applied to the raw video image, but you could have implicit orthorectification, which is then later applied to the velocity results. The only time that you don't have to orthorectify an image is when data is captured perfectly to nadir, so that's perpendicular to the surface of the river, and intrinsic image distortion has been removed from the camera, and that's basically lens distortion. There's two types of orthorectification that can be applied depending on the location of the camera and the number of ground control points available. So if you've got 4 GCPs at the river surface elevation, then a 2D transformation can be achieved. 3D transformations are made when there's large variations of elevation between the GCPs and the river surface. And if that's the case, then a projection has 11 unknown dimensions and can only be solved with more than 6 ground control points. And we tend to say that you want a minimum of 8, an absolute minimum of 8. The more, the better the redundancy. And it's also suggested that you have at least 4 GCPs around or within the immediate region of interest, and that's to achieve the best results. Image manipulation isn't always a step that's required. So the importance of image manipulation is when traces aren't as prevalent as they could be, and programs have a problem detecting and or tracking the traces throughout the process. There's several techniques that can be applied to imagery to enhance tracer visibility. Frequently used enhancement techniques are shown on screen. You've got intensity normalization, histogram equalization, etc. So one of the most important techniques to use, arguably in most situations, would be enhancing the imagery through contrast enhancement steps. So this would simply enhance the brightness between the tracer and its background as to make it stand out throughout the process. In general, an absolute minimum, it's suggested that the imagery is converted to grayscale and then cropped to the area of interest to reduce the unnecessary data processing and noise where possible. The figure that you can see on screen employs each of the corresponding enhancement steps to a frame captured from a drone roughly half a second apart. So at the top of the figure is the raw image, simply grayscaled. The middle section shows how each individual enhancement step affects the image, while the bottom band shows how applying the mix enhancement steps can greatly improve tracer visibility on the river surface. Which takes us on to our third stage of the image velocimetry process, which is that of actually processing the video data through either a PIV or a PTV program. To better understand which method is best for the data you have, I break down the processing into two separate subheadings, and that's founding principles and feature tracking schemes. I'm not actually going to go into too much depth with the foundations of velocimetry, but the general gist of it is that there's things called Eulerian motion, which is used for PIV methods, or Lagrangian motion, which defines PTV methods. So Euler uses fixed areas to determine the movement between grids and particle displacement, whereas Lagrangian tracks individual particles throughout the frame. There's no way of predetermining which technique is better, as both have their advantages and disadvantages. So you've got one limitation that Lagrangian techniques have, is that natural traces are not entirely stable, and the structure is actually capable of deforming or breaking up or agglomerating or even interacting with one another. And the problem is we're not actually yet able to define how those particles interact with one another mathematically, which means it can interrupt or disrupt the process of tracking that feature. A limitation that you've got with Eulerian is the reliability of particles remaining a steady velocity throughout the gridded structure, and that's a basic fundamental to do with its mathematics and its assumptions. The traces have to be at a stable velocity throughout the process for it to track it successfully. So once we've understood the founding principles, it takes us on nicely to looking at the actual feature tracking schemes, such as PIV and PTV. So as I previously stated, PTV-based methods rely on tracking individual particles along a long profile, where they're typically best performing under low seeding density conditions. PIV methods use search and interrogation areas within an image to obtain particle displacements, and they're a lot less sensitive to the transformation of the individual features and can deal with much larger seeding densities. One thing to bear in mind though, especially with PTV, the greater number of traces that are successfully tracked, the higher the probability of producing an accurate representation of the surface velocity. But there is a problem with the number of traces that you track and the processing time or the power that you need to actually run that process. Typical feature detection methods are good features to track. You've got FAST and you've got SIFT, and then the tracking algorithms that you can use are cross correlation, but there's also others such as KLT and variations of the nearest neighbor algorithm. They're all things that are outside the scope for these presentations, but they're something that you can think about and have a look at if you get into more depth with PIV and PTV methods. So once the processing of the data has been accomplished, we can move on to the post-processing stage and either correct the data should it need to or begin applying the data. So the error correction techniques and the applications of PIV and PTV that I'm going to talk about are error statistical analysis and discharge calculations. And there are other applications for surface velocimetry, but these are the discharge is the one that I'm going to talk about for the purpose of this study. For this error analysis of data, it's important to consider two things. That's the detection of erroneous data and the replacement of that data. So good practice would have each output data set checked for spurious vectors and then corrected. Most commonly, a 2D interpolation can be used, but linear or polynomial interpolation can also be used. So I'm not going to go into too much depth on that now because, again, it's a little bit outside of the scope, especially on how to perform these analysis. Sometimes they're built into software and they can do these things for you, and you can play about with each one and see how each one is impacted on the data. Good software to use for that is River. However, if you want to know more about the basics of it, I provide some common statistical corrective methods for both PIV and PTV, those being PIV, penalized, least squares method, Kraigen regression, proper orthogonal decomposition, outlier detection, And for PTV, the Universal Outliers Detection Scheme, or model-based techniques such as Young's 2004 study shown to validate data that has up to 25% of outliers. So there's loads of information out there. You can read the paper that I published to understand a little bit more about them, but all of the references are there and you can read a little bit more on how they work if you want to. But again, like I said, a lot of the software has this built in and allows you to do the detection and replacement of those erroneous vectors automatically. So finally, we're going to talk about some of the applications, and the one I'm going to focus on is discharge, because I believe it to be one of the most important. So to determine discharge from the velocity outputs, it's important to estimate the average depth velocity for a specific cross-section seen within your imagery. Usually to calculate the depth velocity, you need an alpha coefficient, and it's usually estimated to be around 0.85, and it is anything between about 0.79 and 0.91. So we normally just go for the average of about 0.85. But you can go out with an ADCP and actually work out the depth average velocity for your cross-section at the same time as capturing your bathymetry. To determine the area required for discharge calculations, we need to know a measured transect in the middle of the camera's view. And that can be done by surveying where appropriate. So if it's deep, if it's shallow enough, you can get in the water and use surveying equipment. Or like I said previously, you can get in with an ADCP where it's appropriate and it's not high flows and there's no danger to the equipment or yourself. One issue that you might see when trying to calculate discharge through image velocimetry techniques is that the river surface has to have a good spread of traces. And where that's not the case, and you've not got good velocity outputs, it's possible to interpolate or extrapolate measurements using polynomial, cubic, or constant Froude methods, and that's just to fill some of the velocity gaps that we might see on the surface to get a better understanding of the discharge. So that's pretty much everything that you need to know in order to start going out and capturing your own image velocimetry data. At the end of the day, you're just looking to capture a good, high quality still video of a river and its surface, and then have enough information on the dimensions of the river and its bathymetry to able to auto rectify the video in some software. So like I've said several times, this presentation was just touching on the main topics, the main issues, and the paper that I wrote and released last year has all of this information in and more, and it goes into more depth of things. So if you're a little bit confused, have a look at that and it might clear it up for you a little bit more. The next lesson that we're going to go through actually is rendering our own velocimetry results using a software that's freely available and runs on MATLAB code, and it's called River. So any queries on anything that you've heard here in this presentation, please let me know and I'll do my best to get back to you.